Howdy folks, it's me, Mr. Hess. I'm here to show you how to do the problems on the Chapter 9 review worksheet. Okay, so if you look at your worksheet there on problem number 1, it mentions that if AF is 14. Now if you look at our picture here of our circle, AF you'll notice is a radius. Okay, so they're telling us the radius is 14 and they want us to find the circumference. Okay, circumference is found by taking 2 times pi times the radius. So if we just mention that AF, the radius is 14, we're going to plug that in for our R here. So it'd be 2 times pi times 14. Okay, and if you punch that into your calculator and round that to the nearest tenth, they want us to find the circumference to the nearest tenth. Then that answer on this one comes out to 88.0. And yes, please put the 0.0 so that your reader knows that this is a rounded decimal to the nearest tenth. Had the problem asked for an exact circumference, which it did not, but if it had, the exact circumference to this problem means that you would leave it in terms of pi. So see the 2 times 14 back here? 2 times 14 would be 28, and 28 then times pi would be the exact circumference. Okay, so there's the exact one. The benefit of an exact circumference is that when you share this with someone, they can round this now to whatever decimal place they want. They know exactly what the circumference was then. Alright, so that was problem number 1. Alright, on problem number 2, they have you find a whole bunch of missing different arcs in this picture over here. The first arc they have you find is the measure of arc AB. Okay, make sure you look at your notation closely. You know, on problems in this chapter, sometimes they have you find the angles here at the center, or even inscribed angles possibly. So look at your notation. This is an arc, measure of an arc. Okay, so that'd be the measure of this arc out here. Okay, we did learn in this chapter that if the central angle here is 32 degrees, then the arc it intercepts, which is arc AB out here, would be the same measure. So that's also a matching 32 degrees. The next arc they want us to find is BC. All right, now, in this picture, I see this 90-degree angle, so I know that if I take 32 degrees away from 90, that's going to leave me with 58 degrees for that angle there. And again, if that angle at the center of the circle is 58, then the arc it intercepts out here is also 58. So that one is 58 degrees. The next arc they want us to find is arc CD. All right, now I notice that AD here is a diameter. Diameters are your friend. Diameters cut a circle in half, and half of a circle, of course, is 180 degrees. So we know if these two together were 90 here, that means this must be another 90 right there beside it, and the whole thing adds up to 180. So this is 90 degrees. Arc CD is 90. The next arc they want us to find is DE. Okay, DE is this little arc here. Now to get this one, I'm going to use an idea that we've learned previously in geometry, that when you have 2 lines intersect, like these 2 diameters are right here, and you have angles that are opposite one another like that, remember we call those vertical angles. And we know that from the past that vertical angles always match. So 32 here means 32 here, means this arc out here is also 32 degrees. Okay, and then the last one on this problem they asked for is the measure of arc AE. You'll notice that's this part here. There's a couple ways we can get that. You could use the vertical angles idea again if you like, but be careful. This entire angle here is vertical angles with this entire angle there. So you'd have to add together 90 and the 58. Or you could just use the idea too that a full circle adds up to 360 degrees. So you could simply take away all of these other angles. Take away the 32, the 58, the 90, and the 32 again. And if you take all those away, it should match that 90 plus 58, or 148 for that angle, or that arc, I should say. Okay, so that's 148. Now, all these were minor arcs, okay? On the review sheet, they didn't have one where they had you find, say, a major arc on this problem, at least. So, I just want to show you then, if they had said something like this, that they wanted the measure of, let's say, arc ADE. Now, major arcs, you'll notice, use 3 letters. Okay, so in a major arc, if you forget, a major arc is any arc that's going to be more than half the circle, or in other words, more than 180 degrees. And if you follow those letters in that order, ADE, ADE, you'll see that arc goes all the way to there. So you could simply add up all these. You could add up a 32, a 58, a 90, and another 32. Or, a shortcut on this too, you'll notice that this big arc here is almost a full circle. It's just missing the 148. So as a shortcut, you could just subtract the 148 from a full circle of 360. These should come out to the same answer. Okay, and in each of these, let's see what we get here. You get 212 degrees. Just to show you, this one does too. Yep. Carry the 1, 10, 18, 21, 212. Okay? So the main idea, though, in this question, though, is that I want you to learn it and you know, keep in mind, is that all of these are central angles, and a central angle and the arc it intercepts have the same measure. 32, 32, 90, 90, 58, 58, and so on. Now, problem number 3 then uses this same picture, and this time on problem number 3, they mention that that AF, that radius again, is 5. And on this problem, they want us to find the length, not measure, but length of arc AB. So length of arc AB. Okay, now arc length, keep in mind, well, it's different than arc measure. Measure is in degrees, just like an angle would be. Arc length would literally be if you took a tape measure, you know, and measured this, you know, and try to find out how long it is. Okay, so the AF being 5, the radius being 5 is all we really need, other than the measure of that arc as well. You know, we're not finding the measure of the arc, but we're going to use the measure of the arc to find the length. Okay, so here's the formula, by the way. Arc length equals the arc measure divided by 360 degrees. Okay, by the way, that's simply going to tell us how much of a circle we have. You know, like if it was this 32 degree arc here, that's 32 degrees out of a full circle of 360. In this case, it's arc AB we're looking at, which, well, what do you know, is 32 degrees. So that is going to go in over the 360, because that's going to tell us how much of a circle. Now, I got distracted there. The rest of our formula here is you're going to multiply this fraction of the circle times the circumference, which is 2 pi r. 2 pi r would be the distance all the way around. We don't want the full length of the circle. We just want arc AB. So that's why we're multiplying it by this fraction. That's the fraction of the circumference we need. All right, so let's finish filling this in now. 2 times pi times the radius. It was told in the problem AF, our radius is 5. So we're going to put a 5 in there. Okay, and now you just let the calculator do the work. Divide these, multiply by all that. You can round your answer to the nearest tenth on this unless they specify otherwise. In this case, it rounds to 2.8. And if you want to know like a label, if they had initially told us, for example, this was centimeters, which they did not, but if that was centimeters, this would be centimeters as well. Okay, so that's problem number 3. All right, starting with problem number 4, there's a different circle we're going to use on this, which I've already drawn on the flip side here. So we've got this circle. There's the center at P of the circle. So they did give us one central angle. They told us the measure of this arc out here is 86 degrees for arc SV. And this is important too to this problem. They do tell us that the top segment or chord here, RS, and this bottom chord, TV, are parallel. All right, so rather than using the idea that a central angle and its arc match, which in this case that'd be true, you know, this 110 at the center would match this arc it hits out here, 110. But more importantly on these problems, we're going to be using, instead of central angles, this one's going to involve a lot of what are called inscribed angles. Inscribed angles are not at the center of the circle. Inscribed angles are going to have their vertex on the circle itself. Okay, so let's say we're doing problem number 4 here, and they want the measure then of angle PRS. PRS. All right, so let's follow that. We got P here, there's R, there's S. It's that little angle there. All right, now we don't have to use the idea of inscribed angles to find that angle. Instead, I'm going to use this idea. See how PS is a radius and PR is a radius? That makes this an isosceles triangle. And in an isosceles triangle, not only do you have 2 matching legs or sides, but you should also have 2 matching base angles that are across from those sides. So across from this side was the angle I want to find. Across from this one is that angle. I know the 2 of those are going to match. They're going to be the same. So now I could just do some simple math here. I could say, okay, a triangle adds up to 180. There's 110 of it, leaving me 70 degrees to split equally between those 2. So when I split that equally, I get 35 degrees for that angle. So that angle in there is 35. Yeah, on problem number 5, they want the measure of angle VRS. VRS. All right, now here's finally an inscribed angle problem. Okay, if you look, VRS. Okay, it's this angle that goes all the way across there. It's bigger than 35, obviously. See that? Because it's got the 35 within it. Okay, but it is an inscribed angle because its vertex is on the circle, and when you follow it out, it goes all the way out and hits the circle and has an intercepted arc. In fact, that arc it hits is 86 degrees. See it? If you follow that angle out, it hits that arc, 86 degrees. Now, inscribed angles are not going to be the same as the arc. You know how like the central angle is 110, so this arc was 110? But that's at the center of the circle. If you imagine, you know, if I were to pull this back even further, this angle, as I pull this angle back, it gets skinnier and skinnier. It gets smaller. So an inscribed angle is going to be smaller than its arc. In fact, it's exactly half. So we're going to be doing half of 86 for this one. And half of 86, 43 degrees. Problem number 6 wants the measure of angle STV. 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 Again, if you follow them in that order, that's the angle we're looking at. This angle right there. STV. It's an inscribed angle. You can see it comes out and hits that same arc again. The 86 again. Okay, so again, we could just do half of the 86, or if you realize that both this angle and the previous angle both hit the same arc, then they have to be the same as each other. So you could just copy this answer again, 43. On problem number 7, instead of an angle, this time they have us find the measure of arc, RT. So if you look up here, that's this arc right there. Okay, that's what they want us to find. All right, now for this one, we're going to utilize this idea now. The fact that the top and bottom of this, RS and TV, those two chords are parallel. Now, if you remember right, we had a whole chapter back in chapter 3 that dealt with parallel lines and transversals that cross them. And we learned about all kinds of matching angles, like corresponding angles and alternate exteriors and alternate interiors. Okay, well, we're going to utilize that here. If I realize that this top here is parallel to this bottom, okay, and then if I take a look at it, if I run this transversal right there, if I highlight that one, okay, the parallel lines are cut then by that transversal, and notice then that this entire angle here and that angle I marked down here in black are a pair of alternate interior angles. See the Z shape inside the Z at this corner and this corner? Those are alternate interior angles. And if the lines are parallel, these have to match. Okay? So do you see how this one, remember, came out and hit the 86-degree arc? This angle is the same as that one. It's another inscribed angle hitting this arc. So if the angles are the same, shouldn't the arcs be the same as well? If that's 86, this is 86. So the measure of arc, RT, is 86 degrees. You might say we could create a new formula, a new theorem that says that anytime you take parallel lines and you cut through a circle like this, the two arcs at each end in between those parallel chords, those arcs would have to be the same as well. All right, on number 8, they want us to find the measure of arc TV. All right, now look, arc TV is the only arc we haven't found that completes a circle. See that? We got 86 here, 86 there, 110 up there. So if we want to know this last arc down here, we can simply use the idea that a full circle is 360 degrees and take away then these three. Take away the 110 and take away 86, not once but twice. So if we take all of those away from 360, we should be left on this one with 78 degrees for that arc down there. All right, then that gets us up to number 9. Problem number 9 says they want us to find the measure of angle TRV. All right, so let's take a look. Angle TRV. All right, so if you look, it's that angle right there, TRV. It's an inscribed angle. It's got its vertex on the circle. It opens up and hits the circle then across the way down here. And the arc it hits is 78 degrees. So remember, the inscribed angle, though, is only going to be half the measure. So we just got to do half of 78. And we get 39 degrees then for that one. Okay, so again, in this section of problems, really the main thing that I want you to learn here is about inscribed angles, about how this inscribed angle, for example, that we just did, was half of its arc that it hits down here. And inscribed angles, remember, have their vertex on the circle, whereas central angles are at the center, and they match the arc. 110, 110, but here, that's only 39, which is half of its arc it hit down there, 78. So be careful. People get those confused between inscribed angles and central angles. Okay. We're up to problem number 10. And on problem number 10, they have a word problem here. Now, the word problem is going to utilize something from our notes. Do you remember when we had a lesson on this, and one of our theorems said that if you have a chord and if you have, the actual theorem read this: if a diameter is perpendicular to that chord, a full diameter would go like this and be perpendicular. Then the theorem said this: if that diameter is perpendicular to the chord, it's going to split that chord in half, and it's even going to split this arc in half. Now, we're going to use variations of that, okay? You don't actually have to have a full diameter. We could shorten this up, for example, to not even just a radius, but you could even shorten it up like this, where you're not really worried about when it comes down and hits the arc. If you draw any segment from the center of the circle and you draw it perpendicular to a chord, it, again, was guaranteed to bisect that chord, okay? This is all we're really going to use, as well as this. We're going to cap it off. And that segment I just drew, notice, goes from the center of the circle out to the edge. So this is a radius. Okay? And then, of course, this part is the chord that they'll be talking about in the problem. Chord is any segment going from edge to edge of the circle. And then this little part that's represented at a right angle, that perpendicular segment, that we call the distance that the chord is, from the center. Because remember, distance is always measured at a right angle. So this is the distance from the center. Okay, so that's going to help us on problem number 10. I'm not going to write out the problem. You have it there on your worksheet, but they say a chord is 5 centimeters from the center. So there's that part. So a chord is 5 centimeters from the center. And it has the circle has a radius of 13. There's the radius, remember? 13, right out there. Okay, they want us to find the length of the chord. So in the end, we want to know that full length of the chord. Maybe I'll call that X for right now. But before I can find X, which, by the way, remember, is made up of 2 congruent parts, that chord will get split. I'm going to call one of the halves of that chord W and work with that instead, because you'll notice that when we did this, it creates a right triangle. See that right triangle in here? And of course, then, right triangles are famous for the Pythagorean theorem. So if we utilize the Pythagorean theorem, making sure that we put in the hypotenuse for C, which, by the way, in these scenarios, across from the right angle is always the radius. So the radius is going to go in for that C. The W and the 5 are the 2 legs then. I'm going to put them in for the A and B parts. 5 squared is 25. 13 squared is 169. Subtract this over so I can get the W by itself. So we got W squared equals 144. Oh, that's convenient, because when you go to do the square root to get rid of the square here, the square root of 144 is 12. Okay, now be careful. That's not the final answer. Remember, that's W. If that part is 12, this part is 12, the whole chord is what they wanted. The whole chord should be 24 centimeters. This was all in centimeters. Centimeters. Okay, so I'd hate for you to miss a problem because you forgot to double the 12 at the very end. Okay, so that's an important step. Don't forget to do that. Always double check on problems that you found what you're supposed to find. Okay, problem number 11, I believe, is another problem that utilizes this idea again. This time on number 11, it says, suppose a 24-inch chord of a circle is 32 inches from the center. All right, so they said we have a 24-inch chord that's 32 from the center. Remember, there's the distance from the center measured at a right angle. This will be the radius that caps that off. They didn't tell us the radius, so that's probably what they're going to have us find. And, oh, what do you know? Find the length of the radius. Okay, so once again, you'll see we've got our right triangle here. So we're going to use the Pythagorean theorem. Before I could get started on the Pythagorean theorem, though, be careful. Again, just like our last problem, remember when we had to take the 12 and double it to get to 24? In this case, I got to take the 24, this chord, and cut it in half before I start. Because this triangle only uses that half over there, that 12. Okay, so in the Pythagorean theorem, a squared plus b squared equals c squared. I'm going to put in the radius, since it's across from the right angle. It's our hypotenuse. I'm going to put that in for the c. 32 and 12 go in for these, the two legs. 32 squared, I believe, is 1,024. Let me double check on that. 32 times 32, yep. Okay, and then 12 squared is 144. We're going to add those two together. So 1,024 plus another 144 gives me 1168. And by the way, we're adding, remember, because the r is already by itself. You know, sometimes in the Pythagorean theorem, you subtract the one value over. These are already together, grouped together on the correct side. So we're just going to go ahead and add them. Okay, and then, of course, to get rid of a square, we do the square root. So we get the square root 1168. Let's see what we get here. Okay, you'll have to round your answer on this one. It was a big long decimal. You know, you can see it right there. 34 point, if we round that to the nearest tenth, it'd be 34.2. Okay? So that was problem number 11. And 11 and 10, the previous problem, both again use this idea that a chord, the distance a chord is from the center is always measured at a right angle, and when you do that, it splits the chord in half. And then, of course, when you cap it off with the radius, it creates the right triangle. So these involve Pythagorean theorem. All right. That gets us up to problem number 12. Now, problem number 12 uses another different idea here that we covered in chapter 9. It involves tangents. Okay, we got a tangent line that comes in and just touches the circle right there, and then there's a radius given right here of 9 on this problem, and then finally they cap this off and they tell us that just this little part from here to here is 6. Okay, and in the end, they want us to find the length of that last side right there. Now, the 6 is only from here to here. It's not the full length. Although, on a problem like this, we can actually find this full length. Because, after all, this was a radius of the circle. This is also a radius going from the center to here. So these two should match. That 9 we could transfer here, and 9 plus 6 then is going to give me 15 for that entire length. Now, the other thing that's important on this problem is, and that we covered when we covered tangents, you should have learned that a tangent line will always meet at the point of tangent C right there, will always meet the radius at a right angle. So this is a right triangle. And again, of course, since it is a right triangle, we can utilize the Pythagorean theorem. A squared plus b squared equals c squared. Okay, that Pythagorean theorem comes in handy. The one side that we want to find is one of the legs. Across from the right angle, this entire length is the hypotenuse, so that should be put in for C over here. And that 9 is one of the legs as well. All right, so we have x squared equals 9 squared, or 81, equals 15 squared, or 225. Okay, and then here's a problem where, like I was mentioning earlier, where we'd have to do some subtraction. Why do I keep writing the wrong digit there? Sorry. Okay, I got to subtract this 81 to get this x squared by itself. Okay, so now I've got x squared equals, oh, let's see, what is this? 8 from 22 is 14. Oh, that's convenient again. 144 is a perfect square, so when we do the square root of it, we get 12. So there's our missing length up there of that side of the triangle. That tangent line right there to the circle should have a length of 12, that tangent segment. All right, so 13 is another tangent problem. And again, on these tangent problems, remember, one of the key things to learn here is the fact that the segment that's tangent to the circle meets a radius then at a right angle. So in this picture, we've got a circle like this. This is a radius. There's a tangent. So, what I was just talking about. Well, let me label the rest of this. Hold on. There's a right angle here, right angle here. This is 8. This is 2. And they want to know this. Oh, and they mentioned that's a right angle too. Okay, they don't even have to put a right angle for all 3 of these. You should already know a tangent meets a radius at a right angle. Okay? But even if I didn't give you this, or with this, 90 plus 90 plus 90 was 270. That had to be a 90 anyways. So basically what I'm trying to point out, we got a rectangle. Okay, now, the side that they want us to find, notice it's also a radius of the circle. So this radius is going to match any other radii. There's a radius again right there. So these two are going to match. That's another x, you might say. And on a rectangle, we know that opposite sides are the same length. So 8 for that side means that x plus 2 has to add up to 8. Take 2 off of 8 and you're left with 6. So this has to be 6. So there's your answer on that one. That one's actually meant to be a pretty quick and easy one. One other thing that I didn't put on the review sheet, though, that you do need to remember about tangents. Okay, if you have a scenario like this where you've got a circle and you pick a point outside of the circle and draw a tangent, say there, and another tangent up to here. Okay, when you draw multiple tangents from the same exterior point out here, then these 2 tangents are going to have the same length. So if they told you the length of this one was 27, then this one over here would have to be a matching 27. If you remember right, I called this the dunce cap effect. It kind of looked like one of those cone-shaped hats on top of a head. Like here would be it's upside down, but you see a smiley face, and then there's the cone head. Okay, so don't forget that too. I didn't put one of those on the review sheet. I probably should have. All right, that gets us up to the problems on page 2 of the worksheet. Okay, now page 2 of the worksheet deals with equations of a circle. All circles fit into a certain formula for their equations. And that equation this formula looks like this. X minus a, that quantity squared, plus the quantity y minus b squared equals the radius squared. Okay, and if you remember correctly then, the opposite of this, so like this, how this says negative a right now, the opposite of that would be positive a. That's the x coordinate, since it's by the x value here, of our center point. So our center will be located at the coordinates a, and then you do the opposite of negative b, you get positive b. That's the y value for the center point. And of course, r is going to be the radius. But in our formula, that radius gets squared over there on that side of the equation. So on problem number 14, they keep it simple on this one. They simply tell you that the center is going to be located at negative 16.5, those coordinates, and it has the radius has a length of 3. And they want to know, what's the equation? All right, so here we go. The center point, remember again, we just do the opposite of the coordinates and plug them in there into the equation. So the opposite of the x value is going to go together with this x here. So the opposite of negative 16 is positive 16. Don't forget to square it, because after all, this is essentially just the Pythagorean theorem is what it is. But for the y, our y value was positive 5. The opposite of that would be minus 5. So I put that in parentheses and square it. And our radius was 3. Now if I square 3, you see if I square this right now, I'm going to get 9. So I'm going to put a 9 over here. And there's our answer for problem number 14. There's the equation of a circle that has a center at negative 16.5 and a radius of 3. Okay, then the next two problems continue to get a little more complicated. Instead of just giving you the center and the radius and making it real easy on you, on problem number 15, they do give you the center point again. So that doesn't change. They tell you this time your center is going to be located at the coordinates 15 and x value of 15 and y value of negative 17. And then instead of giving you the radius, though, they make you work for it a little bit here. They give you, in addition to the center, they give you a point on the circle. Again, some coordinates of a point on the circle. So it's 17, negative 17 is the point they're giving us on this one. Now, if you think about it, if we have a scenario where we've got a circle and we know the center and we know a point on the circle, you know, I'm just going to pick some random point like right there. If you connect them, notice that makes a radius. So we need to find that radius because that's what we have to use to find our formula. Okay, so if I want to find the length of this radius, knowing these coordinates at the ends, then all I have to do is use the distance formula to find that. Here's the distance formula. x1 minus x2, that quantity squared, plus y1 minus y2, that quantity squared. Now, we can find the radius doing this. More importantly, though, is what we're really going to want to know is what's underneath the square root. Because even if we know the radius, in the end, we're going to square it. And when you square a square root, those two cancel each other. So whatever's under this square root is really the number that's going to go in for the r squared. But we want to go ahead and do that math. Okay, I mentioned when we covered this lesson just recently, do not use the programs in your calculator to find distance on these. Because remember, your calculator would then find some decimal that's been rounded. It's not even an exact value. We don't want to do that. In these problems, we want exactly what would be underneath the square root. So really, you're better off just doing these by hand, or at least plugging into your calculator everything underneath the square root here. All right, so our x values, we're going to subtract them. So our first x value is 15. Our other x value is 17. So we're going to subtract those and square it. Add to that, the y value is being subtracted. So negative 17 minus another negative 17 squared. All right, so 15 minus 17 is negative 2. Okay, notice I left it in parentheses because when you square it, your calculators doesn't like you. Like if you just put a negative 2 squared, it'll say it's a negative 4. That's not true. You have to put it in parentheses so that your calculator knows to square the 2 and the negative. If you don't put it in parentheses, the calculator only squares the 2. Anyways, that comes out to 4. You don't need a calculator for that. Over here, double negative is plus positive. Positive 17, negative 17 give you 0. 0 squared is 0. 0 plus 4 is just 4 again. Okay, so you could go on and even find the radius and say it's 2 if you wanted. Okay, but we're going to turn around, remember, and when we plug it into the formula over here, we're going to go ahead and square it anyways. And 2 squared is that 4 that's underneath right there. That's what we wanted all along, see? Remember I said I just want what's underneath the square root. So that 4 is what's going to be the r squared part. Okay, it's the 2 here already squared. Okay, then remember here's our center point. So this 15, the opposite of positive 15 is negative 15. So the first part of our equation is going to be the quantity x minus 15 squared. The second part over here that we're going to add on is the opposite of the y value. So instead of negative 17, it'll be a plus 17. Okay, and that quantity gets squared as well. So there's the final answer. The equation for this circle is the quantity x minus 15 squared plus the quantity y plus 17 squared equals 4. Okay, there's one more problem. Okay, and on this last one, they decided that this wasn't enough work for you already. They're going to give you a little more work on number 16 to get to your answer. Because this time, what they're going to give us are the ends of the diameter. Ends of the diameter. So they're giving us 2 points then. That's what they mean here. One of them is located at negative 13, negative 6. And the other end of the diameter is at negative 5, 10. Okay, if you want a visual of what's going on here this time, we've got a diameter going right through the center. But all we have is the 2 endpoints here. We know one end is at a negative 13, negative 6. The other end, clear over here, is at negative 5, 10, you might say. Okay, but remember, to write our equation, we need the center and the radius. Currently, right now, we have neither. So the first thing we're going to do is find the center. Okay, on all our previous problems, they'd already given us that center point. But we know in a circle here on the diameter that the center of the circle is right in the dead center middle of the diameter. This is a radius, that's a radius, the two of them match. So all I have to do is find the dead center middle of that, or the midpoint is what we're saying here. Find the midpoint. Okay, so the center of our circle can be found by finding the midpoint of these 2 endpoints here. The formula looks like this. We take the 2 x values, this negative 13, this negative 5, and we're going to average them. We're going to add them and divide by 2. That'll be the new x value. You do the same with the y values. Negative 6, 10. We're going to add them and divide by 2 as well. All right, so negative 13 plus negative 5, that's negative 18. Divided by 2 is negative 9. Negative 6 plus 10 is 4. 4 divided by 2 is 2. Okay, so there's the center. Okay, now we can treat it just like the previous problem. On the previous problem, they gave us the center and a point on the circle. Well, here's the center at negative 9, 2. And look, we've got not one but 2 points on the circle. We got each end of that diameter. Okay, now you don't need both of them at this point. At this point, you would pick out one set of coordinates at the end of the diameter to use along with the center to find the distance or radius, the distance from the center here to the edge of the circle. Okay, I'm going to choose this set of coordinates because this one has more negatives than this one, and I like to try to avoid using negatives. Okay, but at this point, now you're finding distance. Okay, so now that I already found my center using the midpoint, I'm going to erase this work so that I can make some room here to do my work for finding the radius. Okay, finding the radius then is a lot like problem 15 now. We're going to use the distance formula, which looks like this. Okay, and we're going to plug in, now be careful again, we're going to be plugging in these coordinates here. We don't need this one, for example. Although you could have picked that one along with the center. Okay, either one should work. You'll get the same answer, but I just like this one because it's got at least one positive in it. All right, so here we go. Negative 9 minus the other x value, negative 5 squared plus the first y value, 2, minus the second y value, 10 squared. And this whole thing is going to be square rooted. All right, double negative becomes plus positive. Okay, so negative 9 plus 5 would be a negative 4. Okay, when you square a negative, though, this is the beauty of the distance formula, that negative becomes positive. So that's really just 16, 4 squared. Okay, over here, 2 minus 10 is negative 8. Negative 8, again, when we square it, when you square any negative, it becomes positive. 8 squared is 64. 64 plus the 16 gets us up to, what is that, 80? Okay? Now, I'm not gonna bother to find that square root of 80. I'm not going to bother to find, it's going to be some decimal that you'd have to round anyways. The reason I'm not going to is because if I leave it like this right now, square root of 80, when I go to square my radius, when I go to square this now, the square and the square root cancel. So the number I'm left with is just the one that was underneath the square root there, the 80. Okay, so that's my r squared. Okay, and then remember the rest of this is filled in by using the center point. Okay, so the opposite of the negative 9 would be a positive 9. The opposite of a positive 2 is a negative 2. Okay, and there's my final answer. When you write these, don't forget to put these little squares, and don't forget to put a plus in between here. Remember, like I mentioned before, technically it's the Pythagorean theorem. This is like a squared plus b squared equals c squared. Well, there you have it. That's problem number 16. There's your final equation. Let me know if you were confused by any of these, or if you still have any questions. You can contact me by email or send me a text through Remind and let me know you're having trouble, and I'll reach out to you. This is then the last bit of Chapter 9 other than the test itself, so your next assignment on Friday will be the Chapter 9 test. Okay, I may release it even a little bit earlier on a Thursday just to make sure you have a full week, because the 21st, remember, don't forget this, the 21st of this month is the last day to get all tests completed. Turn in any and all assignments. All your work has to be turned in by the 21st. Okay, so I may release the test maybe even a day earlier than I normally would have. So just keep an eye out for that. Alrighty, enjoy your summer, and stay safe.